Okay, so last talk of this session is going to be given by Andrea Montanari from Stanford.
Yes. Okay. I guess I have to start by apologizing twice with the organizers. The first reason is that they had to work really hard to get my title. They sent an exponential number of reminders. And the second is that the title was wrong, so I changed it. So I'm going to talk about graph localization, and this is joint work with my student, Adele Javamart. Okay, so to explain the problem, let me start with the computational chemistry question. You have a molecule. This is actually a caffeine molecule. And you know the composition in terms of atoms, and you know some partial measurements of the distances between the atoms. And the problem is, from these distance measurements, reconstruct the three-dimensional structure. Okay? So this is a practically important question, and the same mathematical question pops up in all sorts of domains. The one that is probably most interesting for this workshop is manifold learning. It happens that many high-dimensional data actually lie on a low-dimensional submanifold. This is the case, for instance, for images of an object taken from a different point of view. This is called an articulation manifold. And standard linear regression or PCA find this manifold if it is a plane or an hyperplane. And manifold learning tries to learn the manifold if this is not a plane, if this is not linear. Okay? And generically, the question here is you are given a cloud of points in some Euclidean space, and you have partial distance measurements between nearby points, and you want to reconstruct the geometry of those points. Okay, actually, I came to this problem from a completely different route, and the route was that I was interested in matrix completion, and there has been quite some interesting theoretical work on that problem. And behind all of these models that people used for matrix completion, there is kind of a big lie. And the lie is the following. You have a low-rank matrix, and you assume that you sample uniformly random entries for this matrix. Okay? And this is, of course, false for localization, but because you only measure nearby points, distances between nearby points. But it's also false for the Netflix problem, right? Because I don't know you, but when I go and rent a movie, I don't rent a uniformly random movie. I have a pretty good idea of which movie I will like, and I rent that one. So this is a case in which there is a correlation between the value of the entry and which entry is revealed. Okay? So I wanted to understand what is the effect of this correlation. And so what I will talk about is actually a very simple. Not that simple, actually, but easy to define model. And the model is the following. You have hypercube in d dimension. D will be some small fixed number, 2 or 3. And you have uniformly random points, n uniformly random points in this hypercube. You connect them with an edge if and only if their distance is below a certain radius, r. What you obtain is a random geometric graph. This random geometric graph is connected if the range is bigger than a constant times log n over n to the 1 over d. Okay? So I will assume that r is bigger than a sufficiently big constant times the same quantity. Okay? So from the scaling point of view, the graph is barely connected. Okay? And so for each edge in this graph, I measure the length, the Euclidean length of the edge. And the measurement that I obtain is noisy, and my model for noise will be adversarial. Right? So there is some nasty guy here that takes the actual distance, and he actually returns me a d tilde whose difference from d is at most delta. Right? So this is the model. And my game, my task, is to reconstruct the point positions from these distance measurements. And the question is, how well can I do it? Is the model clear? So all the rest of this talk will be about just this model, essentially about this model. So of course there is a, given the practical relevance of this, there is huge list of works and contribution of it. This dates back probably to cartography, because people have to solve this problem to place cities on a map. So they do it by triangulation or trilateration, so sequentially. In the sensor network literature, there is this algorithm MDS, multidimensional scaling, that was very popular. Essentially, it is PCA with some bell and twisters. There are algorithms that partition the graph in subsets. The group of Yin very much developed SDP relaxations, and this will be most of the topic of my talk. And there is a whole subclass of algorithms that are really motivated by manifold learning. But in manifold learning, as I briefly explained, the basic question is really to solve this, to a large extent, to solve this localization problem. So despite this long line of work, there is theory, but there is not a lot of quantitative theory, especially when you assume that there is noise and there is finite information. So typically the theory is asymptotic. As n goes to infinity, I recover the correct positions. Okay. So what I'll do is that I'll describe a very simple SDP relaxation for this problem. This is not supposed to be the best one, but is the one that we were able to prove something about, and then describe briefly the ideas of the lower bound and of the upper bound. Okay? So what is the SDP relaxation? A couple of caveats. First of all, of course, if I only have distance measurements, I cannot reconstruct the point positions, because any rigid motion of that points also satisfies the same distances. So I'm trying only to reconstruct positions up to rigid motion, that is translation, rotation, and reflections. Okay? And second, the problem turns out to be, not surprisingly, NP-art. Okay? So we have to deal with some relaxation. So what if I had infinite amount of time for solving it? So what I would try to do is that I would try to find positions position xi for each point, that respects my distance measurements. So that the xi minus xj, Euclidean norm, minus my distance measurements, is at most delta. It is at most my precision. Okay? So I will go over all those solutions. And here I add an objective function that is just minimizing the sum of squares. This is just centering the points. Right? It's just moving the barycenter to the origin. So it's kind of eliminating these invariance under translation. Okay, so this is a nice optimization formulation. Of course, it is non-convex, so I cannot really hope to be able to solve it. Okay? It will have many solutions, many local minima, etc. Okay? So I start by massaging a little bit notation. And okay, it turns out to be very useful to introduce this matrix. Qij is the scalar product of xi and xj. This is the gram matrix of the point position. Okay? If you write my objective in terms of this matrix, this is the sum of qii, of the diagonal element. And the distance between I and j is just xi square minus 2xi xj plus xj square. So this is exactly the same problem as before, so I didn't do anything, basically, right? So the problem is still non-convex and unsolvable. Okay, so just let me still massage a little bit. I write the sum of the diagonal element as a trace, and this linear combination of entry of j, I can write it as scalar product of a matrix Mij and Q, where Mij is the matrix that has 1 on entry ii, 1 in entry jj, and minus 1 on ij and ji. Yeah, so I just, scalar product is just the trace of the product of the two matrices, and I just rewrote once again the same thing. And now, to get the relaxation, I just get rid of this constraint, I replace it with the constraint that Q has to be positive semi-definite. Any gram matrix has to be positive semi-definite, because it's XX transpose. And I just got rid of this. Okay. So my algorithm will be just the following. I solve this semi-definite program. Now this gives me a positive semi-definite symmetric matrix. I can diagonalize it, and I pick the top D eigenvectors and eigenvalues. And those eigenvectors are scaled by the square root of the eigenvalues will be my candidate point position. So what I return. So this is the algorithm. You solve an SDP and then you project on D dimensions. Okay, so the question that I want to ask is how robust is this with respect to noise delta? And there is, previous literature here is 0. So this is our result. So assume that R is a constant times log n over n to the 1 over d. So I remind you, this means that it's essentially a constant above, when it becomes connected, the graph. So I cannot do substantially better than that. Then the distance between my reconstruction and the actual position is bounded by C1 is a constant depending only on dimension. And then there is nr to the d is the average degree of the nodes. Okay, so if this graph is barely connected, this essentially is a log factor, is log n to the 5th. And then there is delta, so as my measurements are more and more precise, this goes to 0, divided by the radius to the 4th. As I get more and more measurements, the construction become more and more precise. So the scaling makes sense. This is in particular saying that if I am, if I have exact measurement and I'm a little bit above the connectivity threshold, I can reconstruct all the positions exactly. So the error is 0. Now, the question is, can I do substantially better than that? And the answer is no, in the sense that there exists an adversarial, set of adversarial measurements that gives you at least that error for this specific SDP. Okay, so the two differ by this factor that is the degree to the power 5th. Okay? Now, this notion of distance I didn't define just not to clutter the slide, but basically is the average distance between the points. Okay. So this is the upper bound and lower bound. So what I'll do now is that I'll try to describe some basic ideas in proving this, actually. Okay, so the lower bound is fairly easy, but it's interesting. So what does the adversarial do? Okay? You want to somehow mess up your measurements as much as possible. So what he will try to do, he will try to use what is the weakness of semi-definite programming. And the weakness of SDP is that SDP doesn't know what is the ambient dimension. Doesn't know that your points lie on a plane. So what the adversary will do is that he will bend the point position. So he will bend the graph. So imagine that, okay, so your graph is drawn on a piece of paper. You just curve the piece of paper by a small radius of curvature. Okay? And if this radius of curvature is not too big, so this is inversely proportional to the square root of the precision. If it is not too big, I can bend the graph without distorting the edges more than delta. Okay? And then what it will do, it will return you exactly the edge length of this bent graph. Now, SDP doesn't know the dimension, so what he will reconstruct is this graph embedding in 3 dimensions, and then you will project it in 2 dimensions. And if you compute the error in the positions, this is, whatever is the lower bound is what you get. Okay? So this is very interesting because it's telling you what is the worst case error. Okay? Now, the upper bound is much more challenging and is more interesting, and is related to rigidity theory, has some connections to rigidity theory. So rigidity theory is a fairly well-developed area of discrete mathematics that deals just with the following problem. Given a graph, is there, and numbers for the edge lengths, is there a unique way of embedding in d dimensions respecting the edge length? So it's just solving the problem of unique reconstruction in absence of error, okay, with exact measurement, okay, noiseless measurements. So in general, the answer will depend both on graph topology and on the point positions. So for instance, this graph, if the reconstruction is unique, you say that the graph is rigid. So this graph is not rigid because you can flip this point around this axis, while this graph is rigid. Now, in fact, people, this is global. People, in fact, study more generic global rigidity, that is a rigidity with respect to a generic set of position, and this has a very nice characterization that took many years to prove, and it says that the graph is generic globally rigid if it admits a stress matrix with rank n minus d minus 1. So this is a very interesting theorem, except that I didn't define most of the quantities of these slides. In particular, I didn't define this crucial stress matrix. So let me tell you what this is. So since my PhD is in physics, I'll tell you with physics. So what is with physics? Imagine that you have this graph, and you put springs on the edges. And now you are free to choose spring constants for this spring. And your game, your task, is to choose the spring constants omega ij in such a way that your embedding is an equilibrium configuration. Okay? So that the force on vertex I is 0. So the force for systems of spring is the sum of the neighbors of omega j xi minus xj. So if you find such spring constants, you can construct a stress matrix by putting, those spring constants out of diagonal by organizing them in a matrix and fixing the diagonal in such a way that the row sum is 0. Okay? So this defines a stress matrix, and stress matrix is directly related to rigidity of the graph. Okay. There is another notion from rigidity theory that is important, and is infinitesimal rigidity, and this has to do with the following. I don't want just to understand whether there is a unique way to embed the points, but I want to understand the following. Can I deform infinitesimally the points in such a way to respect all the edge lengths? Okay? So imagine that you have a motion, so you have velocities at time 0. What happens is respecting the edge lengths means that xi minus xjz square must be 0. So if you take derivative with respect to time of xi minus xj square, what you get is xi minus xj transpose times xi dot minus xj dot. Xi dot is the velocity of point I. So this set of equations has some trivial solutions that are xi dot equal a constant vector plus an antisymmetric matrix time xi. And what does this correspond to? If you think a moment about it, it corresponds to translating and rotating the points. So you say that the graph is infinitesimally rigid if there is no other way to change infinitesimally the point position. So if they are infinitesimally rigid. And also this is fairly easy characterization. This is infinitesimally rigid if the following happens. This is a linear system in the velocity, so you can write it as a matrix plus the point velocities. The null space of this matrix is at least the dimension of the space of rotation plus the dimension of the space of translation. And the graph is infinitesimally rigid if and only if you don't have anything else in the null space. So the null space is exactly rotation and translations. Okay, so now what is the idea with respect, after this detour, what is the idea with respect to the upper bound? Somehow noise in the measurement is equivalent physically to the following. I'm stretching some edges and I'm compressing some other edges. I'm shortening some. And what I want to figure out is how much the graph is robust with respect to this stretching and compressing of edges. So it's quite clear that stress matrix and rigidity matrix will pop out in this, but what you need is not just the rank of them, but you need something more quantitative to bound the error. You need some bounds on the singular values of this matrix. Okay, so now I'll try something, and I don't know if it'll work. Okay. Okay, so this is an experiment, just to a little simulation to show what you want to prove. This is a graph, and I apply forces to this graph, and I pull it. The graph is rigid, but if you give some elasticity to the edges, you can deform it. So you see, this is a graph that you can deform pretty well. And here next to it, I have another graph, and I can deform it with the same forces much less. And this is, looking at it by eye, it's pretty clear why. This graph is much more connected than this graph. Right? And so what we have to do to prove the upper bound is take a random geometric graph and quantify exactly how much you can stretch the random geometric graph. And this turns out to be related to bounding the singular values of these two matrices. So this is the same experiment in equations. This is the energy function that we used. So distance is elastic function plus forces, and these are the equations of motions. So the deformation that you get is obtained by the force times the inverse of this matrix, that is the stress matrix plus the square of the rigidity matrix. Okay? So to bound the deformation, you have to bound the singular values of these two. So how does this pop out, shows up in the proof? At a very high level, you have a solution of the semi-definite program. You have the actual Gram matrix, that is XX transpose. There is a difference between the two. This is this matrix S. And what you do is that you decompose this matrix S in two parts. One is the part that has column space along X or row space along X. And the other is the orthogonal component, that is both column and row space orthogonal to X. And the first part is controlled by the rigidity matrix, and the second by the stress matrix. And these are the basic lemmas. We have a deterministic bounds that bound the orthogonal error in terms of singular values, eigenvalues of the stress matrix, the conditional number of the stress matrix, and then we have a bound on the eigenvalue of this. In particular, the smallest one is lower bounded by essentially r to the fourth, and then you have a bound on the parallel part. Okay, and this involves things like the rigidity matrix. Okay, so in particular, one of these bounds, the one that I like the most is this one. That might not appeal to you so much, so I rewrite it once again. In fact, this bound follows from a stronger one that says that the rigidity matrix is lower bounded by neglecting these guys, r squared times the Laplacian of the graph. Okay, so the Laplacian of the graph is the matrix that has 0 rows minus degree on the diagonal and 1 corresponding to the edges. So it's the adjacency matrix minus the degree. Okay. So it's somehow a very nice characterization of the graph, and it's interesting that this is related to the Laplacian, and this relation is actually a formalization of something that appears in manifold learning literature as a kind of folklore statement, and the folklore statement is that omega should be of the order of L squared. Okay? And this is a formalization of this because the minimum singular value of L is r squared. So this plays the role of one L, and you have the other L there. Okay. So let me, last 5 minutes, discuss briefly, the connection with manifold learning. Okay. So how do most of the algorithms for manifold learning work? You have a data set. Out of this data set, you construct a graph. This is a proximity graph that is obtained by connecting two data points if they are close enough in the high-dimensional space. Okay. And now you can associate to each pair of points on this graph, to each edge, a length just by computing the Euclidean length in the high dimension. Okay, so this is, a manifold is 1,000 dimension. You just compute the Euclidean distance in 1,000 dimension. And what is the idea? The idea is that if this lies on a manifold, this Euclidean distance between, close by points will be very close to the geodesic distance along the manifold, because locally the manifold is flat. So if you look at 2 points that are close, I can approximate the Euclidean, the manifold distance with the Euclidean distance. Okay, so this plays the role of my D tilde, my adversarially chosen distances, and this plays the role of my actual distances. And now I reduce this, in fact, to a localization problem. And what is delta? What is the power of the adversary? Well, delta is r to the fourth. Okay, it's the range to the fourth divided by the square of the curvature radius. And this you understand, right? If the manifold is just flat, then the Euclidean distance is equal to the manifold distance. If the manifold is more and more curved, the two are more different. So if you plug this in our bound, what you get at the end of the day is the following, that the error in reconstruction is upper bounded by this factor that is essentially logarithmic. So let's say it's a constant, divided by the square root of the curvature radius. So is this exciting? Well, in reality, this is not very exciting because it doesn't go to 0 as the number of points goes to infinity. And you understand very well why. Is because the manifold is exactly the adversary, right? So as I explained before, the adversary, what it does, it bends the graph along a manifold, right? But what's interesting here is that this is going down, with the curvature radius, so it's exactly in the case of a plane, okay? Which is not the case for instance, isomap or multiple dimensional scaling. So the reason why this is not exciting is not that our theorem is lousy, it's that the algorithm is wrong. It's the wrong algorithm for this. The right algorithm is this one, is maximum variance unfolding. The fact is that you have to tilt your reconstruction towards flat manifold, right, for solving this problem. So you have to replace the problem before by this slightly more complicated optimization problem. You maximize the point variance subject to the same constraint that we have, and that barycenter is 0. Okay, so what you do is that you relax this, and you get this. You maximize the trace of Q subject to this, and then the matrix being positive semi-definite. So this is a small variation on the previous SDP. We didn't yet prove anything on it, but this is our program somehow to just get this next. Right, so a couple of conclusion. I think that this kind of problems in which we have some geometric structure to be reconstructed from partial measurement is kind of very rich, and it's interesting and challenging. As I said, I came to it from matrix completion because all the introductions in matrix completion have a sentence that says, and by the way, this can be applied to graph localization. So I said, yeah, why not? Let's try. And then I realized that nothing of what has been done for matrix completion can be applied here. So it was a bit frustrating, but interesting. And there are many open problems. Okay? Thanks.
Okay, are there any questions?
Yeah, I said many open problems. I mean, I hope that somehow what we did here is, give some infrastructure for proving, for analyzing these kind of problems, really. But what we shooted for is really the simplest one. But you can put a lot of other, so the question is, you can put other constraints, right? So you can put, one other that you can put is that, if you have 2 points that are not connected by an edge, their distance is at most the graph distance, right? It's at most. If they are not connected, at least you compute the shortest path in the graph, and the shortest path of the graph is an upper bound on the actual Euclidean distance, right? So you can add n square constraints. How much does this improve? I don't really know, right? And the other, do the maximum variance. I think that will help a lot. Yeah.
I think it's kind of related question. So distance matrices are extremely constrained.
Right.
And when you do SDP, you're just dropping. So there's symmetry, the triangle inequality. I mean, a lot of things that this adversarial model and this stretching model is not taking into account. And I wonder if you are not kind of, by putting this, oversimplifying and not really exploiting the structures of a distance matrix.
Again, I think that something that can be put without too much effort would be the linear constraint, like is constraints, like Qij, the distance between I and j, at least this or at most this. Triangular inequality probably is a bit more painful to put in. Again, there is one other limitation that we looked at, adversarial model. Probably if you look at a randomized model of noise, this will have, you will get better bounds, okay? I mean, this is all directions, right? I mean, really, here what is really very, very complicated, I mean, at least painful for us mathematically, was to prove these singular values bounds. Hopefully, once we have that, then we can do other examples, other algorithms. Uh-huh. Yeah, so EUA and others have, they have some theorems, but the theorems are of the form typically, if the graph satisfies this condition and the measurements are noiseless, then you can reconstruct the positions exactly. Now, noiseless is really too much, right?
But you see the same kind of analysis you applied here in your system for diversity?
Yeah, I mean, yeah, I don't know. I hope so, right?
Okay, so we have a break now. That was very nice. Thank you. Very nice.